Let's begin with something so ordinary that it almost disappears from our attention. A glass of water sitting on a table. You don't question it. You don't analyze it. You drink it, wash with it, cook with it. It feels completely natural that water at room temperature is liquid. But physics is not concerned with what feels natural. Physics asks a colder question. Given what we know about molecules, should water actually be liquid at this temperature? Now imagine you are encountering water for the first time with no emotional attachment to oceans or rain or rivers. You are simply a physicist examining a molecule called H(O). It is small. It is light. 2 hydrogen atoms, 1 oxygen atom. If I told you nothing else, just its size and mass, and asked you to predict whether it should be solid, liquid, or gas at room temperature, you would likely say gas. And that would be a reasonable answer, because in the world of molecules, size matters. Light, small molecules tend to move quickly. Temperature, after all, is just motion. The faster molecules move, the harder it is for them to stick together. And if they cannot stick together strongly enough, they separate. When they separate widely, we call that a gas. Let's compare water to a similar molecule, hydrogen sulfide 8s. Structurally, it looks similar. Replace oxygen with sulfur, and you have something close in shape and bonding style. But hydrogen sulfide is a gas at room temperature. It boils at about 6 degrees C. So if chemistry followed a smooth pattern, water should behave similarly. Maybe not identical, but roughly in that direction. Its boiling point should be far below room temperature. Instead, water boils at 100 degrees C. That is not a small deviation. That is a dramatic anomaly. If you plotted boiling points of similar small molecules on a graph, water would stick out like a mistake. It doesn't gently follow the trend. It jumps far above it. And this is where the surprise begins. Because if water behaved normally, Earth at room temperature would not have oceans. It would have a thick atmosphere filled with water vapor. Rivers would not flow. Lakes would not sit calmly in basins. Your glass would not hold a liquid. It would hold nothing visible at all. The default expectation from simple molecular reasoning is not liquid water. It is vapor. So the real question is not, why does water evaporate? The deeper question is, why doesn't it evaporate immediately? Why does it stay together? That is the mystery hiding inside something we think we understand completely. And once you see that the ordinary state of water is actually unexpected, you begin to realize something deeper about physics. The world we consider obvious is often the result of subtle, invisible rules operating beneath our intuition. To understand why water's behavior is unusual, we need to step back and look at how most small molecules behave. Forget water for a moment. Imagine a collection of tiny particles floating freely in space. They are constantly moving, constantly colliding, constantly changing direction. That motion is not an extra feature of matter. It is what temperature means. When we say something is warm, we are really saying its molecules are moving faster on average. Now here is the key idea for a substance to be liquid. Its molecules must attract each other strongly enough to remain close together, but not so strongly that they lock into a rigid structure. A liquid is a delicate compromise between motion and attraction. Too much motion and the molecules escape each other completely. That's a gas. Too much attraction and they freeze into place. That's a solid. Most small molecules don't attract each other very strongly. The forces between them are usually weak electrical effects called dispersion forces or van der Waals forces. These arise because electrons move around, creating temporary imbalances of charge. For a brief moment, one side of a molecule may become slightly more negative, another slightly more positive. That slight imbalance can tug gently on a neighboring molecule, but it's weak and fleeting. Think of it like strangers brushing past each other in a busy train station. There is contact, but no lasting grip. They bump, shift, move on. Because these forces are weak, small molecules with only dispersion forces tend to separate easily when warmed even slightly. Nitrogen gas, oxygen gas, methane, these are all small, lightweight molecules. At room temperature, they have enough kinetic energy to overcome those weak attractions. So they spread out into the space available. They become gases. If you cool them down enough, they will eventually condense into liquids. But you have to go very cold. Nitrogen becomes liquid at about 9 degrees C. Oxygen becomes liquid at about 183 degrees C. These temperatures are far below anything we experience in daily life. So here is the pattern physics would suggest. Small molecules generally have low boiling points. Light mass, weak attractions, easy escape into the gaseous state. Water is small. Water is light. By this reasoning, it should behave like those other small molecules. It should require extremely low temperatures to remain liquid. At ordinary room temperature, it should be flying apart into vapor. And in fact, if you examine molecules similar in size to water, many of them are gases under normal conditions. The trend is consistent. Molecular weight increases, boiling point increases. Molecular weight decreases, boiling point decreases. Water breaks this trend. Instead of boiling far below zero, it remains liquid at room temperature and only boils at 100 degrees C under standard pressure. That is a huge departure from what simple size-based reasoning would predict. So when we say water is just another molecule, that is misleading. In terms of boiling behavior, it is an outlier, a dramatic exception. The puzzle then becomes sharper. The general rule says small molecules don't stick together very well, yet water sticks together remarkably well. Something about it must be amplifying the attraction between molecules far beyond the weak, accidental forces that dominate most other small substances. Until we identify that something, water's everyday existence as a liquid remains scientifically surprising. Expanded 3 part 500 words and remove all narrator headings and brackets. So what is the something that allows water molecules to cling to one another so effectively? To answer that, we need to look carefully at the internal structure of a single water molecule. Not just what atoms it contains, but how those atoms share electrons and arrange themselves in space. A water molecule is made of 2 hydrogen atoms bonded to 1 oxygen atom. But it is not arranged in a straight line. The molecule has a bent shape like a wide V. The angle between the hydrogen atoms is about 104.5 degrees. That geometry matters more than it first appears. Now consider oxygen. Oxygen is highly electronegative, which simply means it pulls electrons toward itself more strongly than hydrogen does. In each OH bond, the shared electrons spend more time closer to the oxygen atom. This creates an imbalance of charge distribution. The oxygen side of the molecule becomes slightly negative, and the hydrogen ends become slightly positive. Not fully charged, not like ions, just slightly imbalanced. But in the microscopic world, slight imbalances matter enormously. Imagine each water molecule as a tiny object with 2 small positive regions and 1 larger negative region. It's not a perfect magnet, but it behaves in a similar way. When 2 water molecules approach each other, the positive hydrogen of one molecule is attracted to the negative oxygen of another. This attraction is called a hydrogen bond. The word bond can be misleading. It is not as strong as the covalent bond holding hydrogen and oxygen together inside a single molecule. But it is much stronger than the weak dispersion forces we discussed earlier. Hydrogen bonds are a kind of middle ground, stronger than accidental attractions, weaker than full chemical bonds. Now here is where it becomes interesting. Each water molecule can form up to 4 hydrogen bonds at the same time, 2 through its hydrogen atoms and 2 through lone pairs of electrons on the oxygen. That means water does not behave like isolated molecules drifting independently. Instead, it forms a constantly shifting network. Picture a room full of people where everyone has 2 hands that can hold others. They grab hands, let go, turn, grab someone else. The connections are temporary, but at any moment, a vast web of linked individuals exists. Water behaves like that. At room temperature, hydrogen bonds are continuously breaking and reforming in trillionths of a second. No single bond lasts very long, but at any instant, a large fraction of molecules are connected to neighbors. This dynamic network makes it much harder for individual molecules to escape into the vapor phase. For a molecule to leave the liquid and become gas, it must break several hydrogen bonds simultaneously. That requires extra energy. More energy means higher temperature. Higher temperature means higher boiling point. And that is the reason water does not follow the simple pattern of other small molecules. Its internal charge distribution and geometry allow it to create a cooperative network of attractions. What is striking is how specific this arrangement is. The bent shape matters. The strength of oxygen's electronegativity matters. The small size of hydrogen matters. If hydrogen were larger, or if oxygen pulled electrons less strongly, the hydrogen bond would weaken. The network would collapse more easily. The boiling point would drop dramatically. So water's liquid state is not a generic feature of small molecules. It is the result of a very particular combination of geometry and quantum electrical behavior. And that combination turns an ordinary, looking molecule into something physically exceptional. Now that we see how hydrogen bonds allow water molecules to hold on to one another, a deeper question naturally follows. Why are these hydrogen bonds in water strong enough to matter so dramatically? After all, hydrogen bonding is not unique to water. Other molecules can form hydrogen bonds too, yet few display such extreme behavior in boiling point density and thermal properties. The answer lies in a subtle convergence of factors that all happen to align in water. First, oxygen is not just electronegative, it is extremely electronegative relative to hydrogen. That means the shared electrons in the OH bond are pulled strongly toward oxygen, creating a significant partial negative charge on the oxygen and a noticeable partial positive charge on each hydrogen. The larger this charge separation, the stronger the attraction between neighboring molecules. Second, hydrogen itself is unusually small. It has only one proton and one electron. Because it is so small, when it carries a partial positive charge, that charge is concentrated into a tiny region of space. Concentrated charge creates a stronger electric field. A stronger electric field means stronger attraction to the negative side of a neighboring molecule. If hydrogen were even slightly larger, its positive charge would be spread over a greater volume. The electric field would weaken. The hydrogen bond would lose strength. A small geometric detail changes the collective behavior of trillions of molecules. Third, the bent shape of the water molecule allows hydrogen bonds to arrange in a three-dimensional network. The 104.5-degree angle between the hydrogen atoms is not random. It emerges from quantum mechanical rules governing electron orbitals. That specific geometry allows each molecule to orient itself so that it can bond to multiple neighbors efficiently. The network becomes extended rather than linear. These factors combine to create hydrogen bonds in water that are unusually cooperative. Each bond is not acting alone. The presence of one hydrogen bond encourages the formation of others nearby. The result is a highly interconnected system. Now imagine slightly weakening this system. Suppose oxygen were a little less electronegative. Or suppose the bond angle were different. Or suppose quantum mechanics arranged electron orbitals just a bit differently. The hydrogen bond energy might decrease by a modest percentage. That modest decrease would have enormous consequences. The boiling point would fall. Water might evaporate at temperatures where it is currently stable. The entire large-scale behavior of oceans, clouds, and climate would change. What makes this uncomfortable is not that we can describe the mechanism. We can. Quantum chemistry explains why oxygen pulls electrons strongly. It explains orbital shapes. It explains charge distribution. What it does not explain is why the constants of nature have precisely the values they do. Why does the electron have the mass it has? Why is the electric charge exactly this strong? Why do quantum mechanical equations yield this geometry instead of another? Physics gives us relationships. It gives us predictive tools. It does not give us ultimate reasons. So when we say water's hydrogen bonding is strong because of electronegativity in molecular geometry, that is correct, but it pushes the deeper question down one level. The strength of hydrogen bonding depends on electromagnetic interaction, which depends on fundamental constants. And at that level, we simply observe and measure. We do not yet derive necessity. Water remains liquid because the numbers in our equations take specific values. Change those numbers slightly, and the everyday world transforms. The glass of water in front of you is not inevitable. It is the outcome of a chain of precise physical conditions extending from quantum fields to planetary climates. Now let's look at something even more unsettling about water. Even after we understand hydrogen bonding and why it raises the boiling point, water still refuses to behave like most substances in one very important way. Most materials become denser when they freeze. When a liquid cools, its molecules move more slowly. As they slow down, the attractive forces between them pull them closer together. When the substance finally freezes, the particles lock into a solid structure that is typically more tightly packed than the liquid form. That is why solid iron sinks in molten iron. Solid aluminum sinks in liquid aluminum. The solid phase usually occupies less volume than the liquid. Water does the opposite. When water freezes into ice, it expands. Its density decreases. Ice floats on liquid water. This is not a small curiosity. It is a profound anomaly. To understand why, we have to look again at hydrogen bonding, but this time in a more ordered way. In liquid water, hydrogen bonds are constantly breaking and reforming. The structure is dynamic and somewhat disordered. Molecules are close together, moving around, sliding past one another while still maintaining many temporary connections. Because the bonds are flexible and shifting, the molecules can pack relatively closely on average. But when water freezes, the situation changes. The hydrogen bonds become more stable and arrange themselves into a crystalline lattice. Each water molecule positions itself so that it forms 4 hydrogen bonds in a roughly tetrahedral arrangement. This creates an open, hexagonal structure. The important word is open. The geometry of this lattice forces molecules to sit at specific angles that leave empty space between them. The structure is rigid and beautiful, but less dense than the constantly shifting liquid. Imagine stacking spheres randomly in a box. If they can move around freely, they may settle into a compact arrangement. But if you force them into a fixed geometric pattern with strict angles between them, you might end up with gaps. That is what ice is, a geometrically constrained structure with built-in empty space. So when water freezes, it expands. That expansion reduces its density. And because it is less dense than liquid water, it floats. This single molecular detail has planetary consequences. If ice were denser than water, it would sink to the bottom of lakes and oceans. Each winter, newly formed ice would sink instead of floating. Over time, bodies of water in cold climates could freeze solid from the bottom up. The insulating layer of floating ice that currently protects aquatic ecosystems would not exist. Instead, ice forms on the surface. It creates a barrier between the cold air and the liquid water below. The deeper water remains relatively stable in temperature. Life survives winter. This behavior is not a general property of matter. It is specific to water's hydrogen bonded structure. And here is what makes it scientifically humbling. This behavior is not imposed by any guiding principle at the macroscopic level. It emerges from the microscopic geometry of electron orbitals and charge distribution. A slight alteration in bond angle or bonding strength would eliminate this anomaly. Ice would sink. Climate systems would shift. Ecological stability would change drastically. The floating of ice is not an obvious or necessary feature of reality. It is a consequence of precise molecular architecture. What appears as a simple winter scene, ice resting quietly on a lake, is actually the visible outcome of quantum mechanics operating with exact numerical values. Up to this point, nothing we've discussed is mystical or beyond scientific explanation. In fact, much of water's strange behavior is understood in impressive detail. We know how to describe the charge distribution within a water molecule using quantum mechanics. We can calculate the partial charges on hydrogen and oxygen. We can estimate the strength of hydrogen bonds. We can model how molecules arrange themselves in both liquid and solid phases. Using supercomputers, physicists and chemists simulate millions or even billions of water molecules interacting over time. These simulations reproduce many observed properties: boiling point trends under varying pressures, surface tension behavior, heat capacity, diffusion rates, even the structure of ice crystals. The mathematics behind these models is not simple, but it is consistent with the laws of electromagnetism and quantum theory. We understand that hydrogen bonding arises from electrostatic attraction between partial charges. We understand that molecular geometry comes from solutions to Schrödinger's equation. We understand that phase transitions follow thermodynamic principles, entropy competing with energy minimization. There is no gap in the laws. The same equations that govern electrons in atoms also govern oceans and clouds. From a scientific standpoint, that is remarkable. It means that the behavior of something as vast as the Pacific Ocean is, in principle, reducible to interactions between electrons and nuclei obeying quantum electrodynamics. But there is an important distinction between understanding the laws and understanding the consequences in full detail. Water is notoriously difficult to model with high precision. Small changes in intermolecular potentials can produce noticeable differences in predicted properties. Accurately capturing the collective behavior of hydrogen bond networks remains computationally demanding. Even today, water is one of the most studied and challenging substances in physical chemistry. It has anomalies beyond density and boiling point. It has unusually high surface tension, which allows insects to walk across it. It has an exceptionally high heat capacity, meaning it absorbs large amounts of energy with only modest temperature change. That property stabilizes Earth's climate. Coastal regions remain moderate because oceans store and release heat slowly. Water also has a complex phase diagram. Under different pressures and temperatures, it forms many distinct crystalline ice structures, not just one type. At high pressures, entirely different arrangements of molecules appear. Each phase follows from the same hydrogen bonding rules, but in ways that are not always intuitively predictable. So what do we truly understand? We understand the mechanisms. We understand the forces. We understand the equations. What we do not always possess is intuitive clarity. Our brains evolved to track falling objects, not to visualize electron probability clouds. When we say we understand water, we often mean that we can compute it, predict it, and experimentally confirm our predictions. But that kind of understanding is mathematical, not instinctive. Water is simple in chemical composition. 2 hydrogens, 1 oxygen. It is not simple in behavior. The gap between microscopic laws and macroscopic experience is where complexity lies. And water occupies that gap in a particularly stubborn way. So while physics explains why water is liquid at room temperature, the explanation runs through layers of abstraction, quantum fields, charge distributions, thermodynamic statistics that are far removed from everyday perception. We know the rules. We can apply them successfully. But the richness of the outcome reminds us that even when the laws are simple, their consequences can be extraordinarily intricate. Even with all this knowledge, there remains something slightly unsatisfying about the explanation. We can trace water's behavior to hydrogen bonding. We can trace hydrogen bonding to charge separation. We can trace charge separation to quantum mechanics and electromagnetism. At each step, we have equations that work. They predict experiments with impressive accuracy. And yet, when we ask a deeper, why? The ground becomes less solid. Why does oxygen have exactly this electronegativity and not slightly less? Why does the electron have precisely its measured mass and charge? Why is the strength of the electromagnetic force what it is, rather than a few percent weaker or stronger? Physics, as currently formulated, does not answer those questions. It describes relationships between quantities. It does not explain why the fundamental constants take their specific numerical values. If the electric charge were slightly different, hydrogen bonds would change strength. If electron mass shifted, atomic sizes would change. Molecular geometry would adjust. Water might no longer remain liquid at the same temperatures. The familiar phase diagram could look entirely different. This realization leads to a subtle intellectual discomfort. Water's properties are not just consequences of general principles like things attract. They depend quantitatively on very specific numbers embedded in the structure of physical law. We observe those numbers. We measure them with extraordinary precision, but we do not derive them from something deeper, at least not yet. There are theoretical efforts, of course. Physicists search for unified theories that might reduce constants to inevitable consequences of symmetry or deeper structure. Some speculate about multiple possible universes with varying constants. But speculation is not explanation. Until a testable framework emerges, we remain in a position of description rather than ultimate justification. Water then becomes a reminder of the limits of explanation. We can explain how hydrogen bonding works. We can explain how it produces a network. We can explain how that network raises boiling point and lowers density in ice. But when we ask why the microscopic parameters are tuned just so, we confront the edge of current knowledge. There is also another layer of uncertainty. Even with known laws and constants, predicting collective behavior is hard. Many body systems, systems with vast numbers of interacting particles, produce emergent properties that are not obvious from individual interactions alone. Turbulence in fluids, for example, remains one of the most challenging problems in classical physics. Water flowing through a pipe can exhibit chaotic patterns that defy simple analytic description. So there are 2 kinds of not knowing. One is fundamental: why do the constants of nature have their specific values? The other is practical and emergent. Even given those constants, how do trillions upon trillions of interacting molecules produce the precise large-scale behaviors we observe? In both senses, water humbles us. It is chemically simple but mathematically rich. It is familiar yet conceptually deep. It is fully governed by known laws, yet those laws, when unfolded across vast numbers of particles, produce layers of structure we are still mapping carefully. The glass of water appears ordinary because our senses compress complexity into simplicity. We see a smooth surface and call it calm. Beneath that calm surface is a restless network of charges and bonds forming and dissolving billions of times per second. What we don't know is not mystical. It is simply the frontier between description and deeper origin, between calculation and complete comprehension. Water sits quietly at that frontier. There is another reason this subject is difficult for us, and it has less to do with equations and more to do with the way human intuition works. Our brains did not evolve to understand molecules. They evolved to understand medium-sized objects moving at moderate speeds, stones, trees, flowing rivers. We are comfortable thinking about solid things pushing against each other. We struggle when the explanation shifts to invisible electric fields and probability distributions. When you look at water in a glass, you see a continuous substance. It looks smooth, unified, stable. Your mind treats it as a single thing, but physically, it is not a single thing at all. It is an enormous collection of discrete molecules, each moving, rotating, vibrating, constantly colliding. Even that description is incomplete because molecules themselves are not tiny billiard balls. They are patterns of probability, regions where electrons are more likely to be found. The solidity we perceive is the result of electromagnetic repulsion between electron clouds. What feels like a firm surface is mostly empty space structured by force fields. This is not how intuition pictures matter. We prefer solid objects with clear boundaries. Physics tells us that what we call solid is actually a stable arrangement of dynamic interactions. What we call liquid is a slightly less constrained arrangement of those same interactions. Water's behavior exposes the gap between intuition and reality. When we hear that a small molecule should be a gas, that makes sense in abstract reasoning, but our daily experience contradicts it. We see oceans. We feel rain. We boil water in a kettle. The liquid state feels natural, inevitable. It is not inevitable. It is a balance between kinetic energy and intermolecular attraction. That balance exists because of precise quantitative relationships. Shift them slightly and our intuition would have evolved in a very different environment. Perhaps one where liquid water is rare or non-existent. We also struggle with emergence. We tend to believe that if we understand the parts, we automatically understand the whole. But large systems often exhibit behaviors that are not obvious from the properties of individual components. A single water molecule does not have viscosity. It does not have surface tension. It does not have a boiling point. These are collective properties arising from interactions among vast numbers of molecules. Surface tension, for example, emerges because molecules at the surface of a liquid have fewer neighbors and therefore experience a net inward pull. That simple imbalance, repeated across trillions of molecules, creates a measurable force strong enough to support a small insect. Our minds do not naturally think in terms of trillions of simultaneous interactions. We simplify, we compress, we build mental shortcuts. Those shortcuts work well for survival. They do not work well for molecular physics. So when we say water should be a gas, we are applying a simplified pattern. Small molecules equal weak attraction equal low boiling point. That pattern is generally reliable. Water violates it because it adds a cooperative network of hydrogen bonds that our simple mental model did not include. The deeper lesson is that reality does not conform to our intuitive categories. It conforms to mathematical relationships. And mathematics, unlike intuition, does not care what feels ordinary. Water's liquid state feels obvious only because we were born into a universe where the constants allow it. If those constants were different, our intuition would have adjusted to a different normal. What we call common sense is simply adaptation to specific physical conditions. Water quietly reveals how fragile that sense of normality really is. Imagine what would happen if hydrogen bonding in water were slightly weaker. Not dramatically weaker, not by half, just a small reduction in bond strength. The consequences would ripple outward in ways most people rarely consider. The boiling point would drop noticeably. At room temperature, more molecules would have enough energy to escape the liquid into the gas phase. Water would become more volatile. Oceans, lakes, and rivers would evaporate much faster. Clouds might form and dissipate in entirely different patterns. Rainfall could become irregular, and the climate systems we rely on for stability might shift drastically. Even a small tweak in molecular interaction would cascade to global effects. Water would no longer be the stable liquid that supports life as we know it. Aquatic ecosystems would struggle or collapse. So much of biology depends on the slow, reliable movement of water in liquid form. Plant cells rely on water for nutrient transport. Animals rely on it for temperature regulation and metabolic processes. Our entire planet is tuned to the specific balance that hydrogen bonding provides. This is why water is often called life solvent. The phrase is true not just metaphorically, but physically. Its ability to remain liquid over a wide range of temperatures, its high heat capacity, and its density behavior all arise from those hydrogen bonds. Alter the bonds slightly, and that capacity disappears. Life itself becomes precarious. Yet this is not an argument about destiny or design. Physics does not explain why the constants have the exact values they do. It describes what happens once the constants are set. We can model consequences, but we do not know why nature chose these particular numbers. That distinction is crucial. Observing that water is liquid does not require metaphysical explanations. It is simply the outcome of specific parameters in quantum mechanics and electromagnetism. Even more striking is how delicate this balance is. Molecules are constantly moving, vibrating, and exchanging partners in a ceaseless microscopic dance. Any single water molecule experiences dozens of collisions and interactions every second, yet collectively they form a liquid that behaves as a coherent, continuous substance. A small change in molecular structure, electron distribution, or bond geometry would disrupt this collective coherence. The ordinary stability of water is an emergent property of enormous numbers of microscopic interactions, not a guaranteed feature of chemistry. This sensitivity extends beyond hydrogen bonding. Ice's unusual expansion upon freezing is another demonstration. If the crystalline lattice were slightly different, ice would sink, changing global patterns of seasonal freeze and thaw. Entire climate systems rely on these delicate molecular details. What we perceive as a calm, unchanging lake is in fact the visible result of precise quantum mechanical forces operating trillions of times every second. Water's properties illustrate a profound principle in physics and chemistry complex. Large-scale behavior emerges from simple rules applied across enormous numbers of components. Trillions of interacting molecules give rise to the physical properties we observe: density, surface tension, heat capacity, boiling point. But these properties are far from obvious from a single molecule's perspective. Emergence turns simplicity into complexity, predictability into delicate stability. Considering this, the ordinary glass of water becomes extraordinary. Its liquid state is not inevitable. It is the outcome of precise physical laws acting over countless interactions, delicately balanced to maintain stability in the face of thermal motion. The fragile balance of forces that keeps water liquid is not obvious, yet it underpins almost every aspect of life on Earth. The everyday presence of water is a reminder that what seems normal and guaranteed is often the result of finely tuned interactions at the smallest scales of nature.